Hello, this is Mr. P, and today we're going to be talking about polynomial functions. By the end of this section, we want to be able to sketch these curves as well as find the zeros to the polynomial functions. One thing we do want to say about the graphs is that they are continuous and smooth for all polynomials. For example, if we take this as an example graph, we have what looks like our cubic function. We should recognize that as our cubic function, but it could be a high order polynomial as well. Matter of fact, the number of directions of the graph of a polynomial, in this case we have increasing, then it takes a turn and goes decreasing, takes a turn, goes increasing. So that would be up, down, up would be 3 directions. That means this has to be at least a third degree polynomial in order to have this graph. Another thing to notice is that the number of turns has to be 1 less than the number of directions. So it starts out going in some direction. We read these left to right, like we always read our intervals. And we're starting out in an increasing direction, and then as soon as we make a turn, you now have a different direction. So your number of directions will always be 1 more than the number of turns, or the number of turns will be 1 less than the number of directions. Another example of a polynomial would be this one. Here we have 1, 2, 3, 4, 5 directions, so this is at least a 5th degree polynomial. And you'll see polynomials will model many natural phenomena and also many things we find in business and economics as well. Now let's take a look at something that is not a polynomial. This graph would not be a polynomial because as it's going along, it gets to this point and then it jumps down to another point on the graph. Therefore, we say this one is not continuous. If you're drawing this graph with your pencil, you would need to lift your pencil off the paper in order to continue drawing the graph. That makes it not continuous and not a polynomial. And also you could have a situation like this where you're coming along. This is our absolute value graph. You get to a point and you make a sharp turn. That sharp turn, or a cusp as it's called sometimes, would make this not a polynomial as well, and because it's not smooth. So it has to be continuous and it has to be smooth, and then you have a polynomial. Now if we look at what we call the leading coefficient test, we're going to try to do a little detective work and be able to sketch the graph of a polynomial based on its equation. Well, we can see as x moves without bound from the left to the right, then the leading coefficient, which is this a sub n when you write it in algebraic form, the leading coefficient, which is the coefficient of the term with the highest exponent, that will give us some information about the graph. First of all, the leading coefficient only tells us what happens with the right side behavior, the end behavior on the right side, but then we can use that to find out some other stuff as well. For example, if a sub n, which is our leading coefficient, if that is greater than 0 or positive, then the function will increase. It will approach infinity as x approaches infinity. Now, x approaching infinity means we're going to the right, so the end behavior on the right side of the graph is that it will go up. Positive infinity is up. Now, as opposed to if a sub n was negative, then again, as we're going to the right, because this leading coefficient test only tells us what happens on the right side of the graph, this function will go down as x approaches infinity to the right. Now, the reason this happens is, if you think about it, you have a polynomial, which means all these other terms have a smaller degree than this first term. Therefore, as x gets very large, this first term dominates the rest of the terms. The magnitude of that first term is huge because that's the one that has the highest exponent. And therefore, the a sub n is what dictates whether it goes up or down, positive or negative. So that first term overshadows all the other terms and really determines what happens with your end behavior. Now, once you know the right side end behavior, you can also find what's going on the left. For example, if n itself, being the degree of the polynomial, the highest exponent will give you the degree of the polynomial. If that degree is odd, then the end behavior is in opposite directions. That means that if you're going up on the right side, you'll be going down on the left side. If you're going down on the right side, you'll be going up on the left side. And as you might guess, if n is even, then the end behavior is the same in both directions. So the odd or even of the degree doesn't really tell you what happens on the left. It just tells you whether it's the same or the opposite of what's happening on the right. And to look at this visually, let's say when n is odd, you would have a situation like this, that if your end behavior is increasing on the right, then since n is odd, you must have it decreasing on the left. And likewise, if n is even and your end behavior is increasing on the right, then you must have it also increasing on the left. So with this little detective work, you can easily tell what's going to happen with your end behavior for all your polynomial functions. Now, continuing with finding out more information about our polynomials, the n being the degree of the polynomial, that means that we will have at most n real zeros. And remember, zeros of a polynomial function is where the value of the function is 0, or graphically that is where it crosses the x-axis. And we spoke earlier about if you have the n being the degree of the polynomial, that is also going to be how many directions you can have, the maximum number of directions. So there are going to be at most n minus 1 relative extrema, because the relative extrema occur when the polynomial turns from increasing to decreasing or decreasing to increasing. And there's got to be one less turn than there are directions. Now, regarding the zeros of the polynomial, there are some things we can say about them. If we have a polynomial function, and we're dealing with real numbers here, so a is a real number, then all 4 of these statements are equivalent. They are saying the same thing. First of all, if we say a is a 0 of the function, then that is also the same as saying a is a solution of the polynomial equation f of x equals 0. So to find a 0 of the function, you can set the equation equal to 0 and solve for x. That is also known as a solution. And they don't show it here, but a lot of mathematicians also call that a root of the function. So 0, root, and solution all mean the same thing. Matter of fact, that value a would also be an x-intercept of the graph, because we know a comma 0 is going to be where the graph touches the x-axis. And number 3 is very useful to us. We'll be using this a little bit later. Is that if a is a solution of the polynomial, or a 0 of the function, then x minus a is a factor of the polynomial. We'll be exploiting this fact in order to be able to factor things that we till now haven't been able to factor. And one little thing just to plant the seed is the intermediate value theorem. And basically it's saying that if you have 2 numbers a and b where a is less than b or b is greater than a, whichever way you want to think of it, then if the values of the functions at those 2 inputs, in other words, f of a does not equal f of b, then on some closed interval, on the closed interval from a to b, f will take on every value, since we know it's continuous and smooth, it will take on every value between f of a and f of b. Now, the reason that's useful to us is that helps us to prove that there is an existence of a 0 of the polynomial. In other words, if f of a is negative and f of b is positive, and we say the function takes on every value between those 2, then at some point between a and b, we are going to have a 0. The value of the function will equal 0. So this is something we're going to be using that's going to help us find those zeros of the polynomial functions. So I just want to give you a little preview of that. All right, now once we have zeros, there is what's called repeated zeros. If you have a polynomial and when you factor it fully, sometimes you get a factor shows up more than once. In other words, x minus a being the factor, that could have an exponent on it. The exponent they're using is k. And if k is greater than 1, then that means we have what's called a repeated zero. And we say k is the multiplicity of that zero. And that does give us some information about the graph. So factoring these polynomials will also help us to figure out what the graph looks like. It turns out that if k is odd, the graph is going to cross the x-axis at x equals a. Remember, a would be the value of x that causes the parenthesis to be 0, so that would be a solution or a root or an x-intercept. So it's going to cross if it's odd, and it's going to touch and go back the same way it came from if it's even. So when k is even, when your multiplicity is even, then the graph won't actually cross the x-axis, but it will touch it at the x-intercept and then turn back the way it came. So let's actually look at an example problem showing this. They want us to find all the real zeros and relative extrema of this equation. And we're going to show both an algebraic solution and a graphical solution. Now, algebraically, this is just a matter of setting the equation equal to 0 and then factoring it. That will give us the zeros of the equation. So we take our original equation, we're going to set it equal to 0, so negative 2x to the fourth plus 2x squared equals 0. We factor out what's common, and then we should recognize that we still have a difference of squares, so we factor that as well. And we get these three factors. One of them has a multiplicity of 2. So this gives us some important information here in fully factored form. What it tells us is that the zeros are going to be the value of x that cause each factor to be 0. So for the first factor, that would be 0 when x is 0. The next factor would be 0 when x is 1, and the next factor would be 0 when x is negative 1. So 0, 1, and negative 1 are the zeros, which means the intercepts are 0, 0, 1, 0, and negative 1, 0. These are the three x values, and of course the y values have to be 0 for an x-intercept. Now looking at the graphical solution, and I'll just show you the printout of the graph. Viewing it on a window from negative 3 to 3 on your x's and negative 2 to 2 on your y's, this is what your graph would look like. And you see it also shows the same x-intercepts, negative 1, 0, 0, 0, and 1, 0. Now just to show you how we arrived at these, let's go ahead and pull up the calculator. And we're first going to look at is negative 2x to the fourth plus 2x squared. So let's go ahead and put that into our calculator. Now, of course, we're always going to check our mode first, make sure we're in the correct mode, which we are. Then we're going to go to y equals, make sure that your stat plots are not on. And here we want negative 2x to the fourth, and then plus 2x squared. And rather than try to figure out a window, let's just go ahead and use the window they used. So going to our window settings, this is the settings for the standard window, but I'm going to do negative 3 to 3 for the x's, and then I'm going to do negative 2 to 2 for the y's. And whenever your ratio of x to y is 3 to 2, then you're going to have you're not going to have a distorted view of your graph. You're going to have a realistic view of your graph, not stretched or distorted. Because physically the window of the calculator is 3 by 2 approximately. It's within a pixel or so of 3 by 2. Alright, so looking at our graph, I'm going to press graph, and you see we get that same graph. Now if we want to actually calculate these intercepts, we can do that. It looks like it goes through negative 1, 0, looks like 0, 0, and looks like 1, 0. But if we needed it to get confirmation of that, we're going to go to second trace. And I'll just show one of these. I'll do the leftmost intercept. And for that, we want to find the 0. Remember, intercepts are the zeros of the function. So you can either arrow down and hit enter, or just hit the number 2. Now it's going to ask for left bound, right bound, and guess. Well, to capture this 0, I want to come up with some interval that's going to capture just that x-intercept. So let's say from -2 to -1/2 should definitely capture that. So left bound, I'm going to say -2. And then right bound, I'm going to do -0.5. And then the guess doesn't matter. I'm just going to hit enter. And there's my 0. It's -1, 0 is that first x-intercept, which is confirmed by this graph here. So you can do that for each of those 3. And then to find the maximum, because it did ask find the relative extrema as well. So to find the relative extrema, we're looking for that point where it hits the top. So that's definitely to the left of 0. So I'm going to say, when we go into our second trace, which is the calculate menu, this time we want a maximum. That first one is going to be a maximum point. So I'm going to say choose option number 4, which is maximum. Now left bound, I want to capture this point, which looks like it's somewhere between -1 and 0. So I'm going to say left bound -1, right bound 0. Notice how it does give you the arrows for feedback as to the interval that's trying to capture that maximum. And guess doesn't matter. We can hit enter, and it gives us the maximum right there, which is the same numbers they got here, although they rounded their numbers. We're getting the same values. Alright, so that would be using the graphing calculator to find both the zeros and the relative extrema. And remember, relative extrema just means locally. It's a local minimum or a local maximum. Alright, let's move on to doing some curve sketching. Here they want us to sketch the graph of 3x to the 4th minus 4x cubed by hand. And the steps for this is we're going to use some of the detective work that we've been working on. So number 1, we're going to apply the leading coefficient test. Now the leading coefficient here is positive, and that means on the right side of the graph, I know that this goes up on the right side. So my end behavior as x approaches infinity is going to be f of x approaching infinity. So the graph is going up as you go to the right. Now, our second thing is we want to find the real zeros of the polynomial, although, well, we're skipping the left side. We do know the right side goes up, and also the degree of the polynomial is 4, so that makes it an even degree, which means on the left side it's going to be doing the same. So left and right side are both going to be going up for their end behavior. And now finding the zeros of the polynomial, we can first factor that. And if we factor, it's a pretty easy one to factor. X cubed is common to both terms, so you factor that out, and it can't be really factored anymore. So you have a 0 of 0, because the value of x that causes the factor to be 0 is going to be your root or your 0. So the first one is going to be 0, and the second one is going to be 4/3. And if you don't notice that as being 4/3, just set that parenthesis equal to 0 and solve for x. So looking at what we know so far, we know that to the right it's going up, to the left it's going up, and we know we have 2 zeros. We know it's going to hit the x-axis at 0 and at 4/3. Now the multiplicity will also tell us something here. Notice how both of these are odd multiplicity. The first factor has a 3 as its exponent, which is odd, And this factor, although it doesn't have an exponent, is assumed to be 1, which again is odd. So in both of these spots, it will be crossing the x-axis. So knowing all that, we just simply need to plot a few additional points. And we can do that with a table of values. Pick some x's that you have these two critical points here. So pick an x to the right of it, pick a couple between them, and pick something to the left of it. And when we do that, we get these values. If you add those to your graph, then you can draw your graph by simply connecting through those known points, and you get a graph approximately like this. So plot the few additional points, some a little left, some a little right, some in between, and that way you'll get the general shape of your graph. All right, let's look at finding zeros of a polynomial function. So this is our example problem. Find all the zeros of f of x as x cubed minus x squared minus 2x. Again, we're going to do this algebraically, and we're also going to do it graphically. Algebraically, we're simply going to factor this. So we're going to take our polynomial, set it equal to 0, and factor. First, all of these terms do have x in common, so we factor out the common x. And then we have a trinomial with a leading coefficient of 1, so we can go right to the double bubble, which is 2 parentheses. To get x squared, you have x times x. And then we want factors of -2 that add up to -1. And that would be -2 and +1. The product is -2, and the sum is -1. And once we have that, we can then make our analysis that the real zeros are going to be the values of x that cause each factor to be 0. So for the first factor, which is just x, that would be 0 would cause x to be 0. Here, 2 would cause that parenthesis to be 0, and -1 would cause that parenthesis to be 0. So the zeros are 0, 2, and -1, which means the x-intercepts are 0, 0, 2, 0, and -1, 0. Now putting this into the calculator, we can verify the exact same numbers. I'm not going to show you the procedure because we already went over that, but this is what the graph actually looks like. And if you go to second calculate and look for the zeros, you'll find these are all the correct numbers as well. All right, with that, we're going to end this section of notes and keep working on the polynomial functions, and we're done.